To Precalculus 1. Today we will be talking about polynomial function, and we will start polynomial functions with the definition of polynomial functions, where this p of x stands for polynomial in terms of x, of a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth plus dot 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 plus an x to the n. So as long as we have the integer numbers for these n's, we will have a polynomial. We always have to have that polynomial end, so you can't put 3 dots afterwards. It has to end with whatever the highest exponent is that you need to go to. So now I'm just going to quickly show this over here. This takes all of the polynomials that you ever learned so far and then the future ones. So if you cover everything, you just have a0. That's a constant function. So let's say y equals to 3. And then if you keep the first two terms, what do you have? What is that?
Polynomial.
Yeah, binomial, but which one is it? This in particular. What is that? X to the first power. You're used to seeing it with different letters, but yes, linear. Y equals mx plus b. There it is. Y equals mx plus b. Right there. mx plus b. mx plus b. Quadratic. ax squared plus bx plus c. Cubic. Quadratic, right? So, depending on what your highest exponent is, you have all of those, which you learned so far, and then many more, which will be there down the line. So now, today we're supposed to learn how to graph or sketch a graph of pretty much any one of these. We'll learn some patterns and things. So let's start first by reviewing those which you already know. So if I start by writing y equals to 3 and graph that one, I will have 1, 2, 3, and that's just the horizontal line which you are used to, right? So that's a polynomial, and that will correspond to the case with just a0 is taken in consideration, and if it's 3. Another example would be y equals, I don't know, 2/3 x plus 1, which would be the linear if you keep first two terms. And you can graph that one as well. You start at plus 1. Let's go half a unit. So that's 1. Go 2 units up and 3 units over, and then connect. So you see that's the linear line that you know. If you keep 3 terms, y equals, I don't know, 3x squared minus 2x plus 5, then that one is going to be some kind of quadratic. It's not going to go through origin. So I'm just going to put whatever quadratic. And you might have some exposure to the cubic one. So I don't know, 4x cubed minus 2x plus 1, whatever. I dropped the x squared term. It doesn't really matter. Actually, you know what? Let's just do the basic one. You know that one. Just write x cubed. And that one looks like this. All right. So now I want to point attention to the edges of these functions which have arrows. That arrow says that the behavior that the function have will continue in the same fashion forever. That's what the arrow is for at the end. So a linear function will forever go up at this slope. See you next week. So we are going to examine this. We're going to call it the end behavior. And we're going to memorize cases from a chart so that you can have your ends for each of the polynomials. And then we're going to do something with x-intercepts and roots. And we're done. So end behavior. We start with the chart. So these are the 4 behaviors we have. At the ends. And in calculus, you would see that as this one is y goes to infinity, and this is y goes to negative infinity, and this is x goes to negative infinity, and x goes to positive infinity, not just infinity. So what happens is, if you look at this chart, and you look at, I'll draw another one. I hope that you see that this way is negative infinity on x, and this way is positive infinity in x. So you can see that the chart fits very well. If you are going to positive infinity in x this way, you see that this arrow is this arrow here. And this one is that one. If you go to negative infinity, you go to negative infinity on y and on x. So end behavior are these simple 4 arrows, and you will always have to have one of those at the end. Now, since you are in precalculus, and we are not going to use limit definitions from calculus, you will have to also remember the end behavior through another feature or chart. It looks like this. Yeah. So you can have a situation like this. Well, actually they use the dot lines because function will do something here in between. And like this. So this is when function, well, exponent. So if the exponent is even, both end behaviors of a function look the same way. Which way they look, up or down, depends on a. So if a is larger than 0, looks up. If a is less than 0, looks down. So now, if the, I forgot the next over here, exponent odd, if the exponent is odd, what's going to happen then? It's going to experience this behavior for a larger than 0, and for a smaller than 0, it's going to look like this. Now observe, I'm putting these dots in the middle of the polynomial because We don't know whether it's a quadratic or a cubic, or we don't know which one it is. I'm just going to say that a linear line has only one form. Quadratic is a U shape, but cubic already has multiple forms, right? He has this one and it has that one. And then the fourth degree is going to have this one, but it's also going to have this one. It's another possibility. So you have a lot of different types of curving in the middle, right? That's the part. So you have to be careful a little bit with that. So now let's take a look at an example so we can understand the example. Let's say y is equal to negative 3 x plus 1 squared minus 2. And the question is to graph this to the best of our abilities, right? And we're not using the, well, leave it. So what do I have? I have x squared. I know that I can solve this problem by simply shifting and moving stuff around, right? We can do it that way. But look what I have. I have that a is equal to negative 3. If a is equal to negative 3, that's less than 0, which means that a less than 0, we are operating in this column. So it's going to be one or the other. One or the other from those two graphs for the end behavior. So what do you do for a less than 0? What do you do? This is a is less than 0, so it's either going to look like this or it's going to look like this. These interruptions are if the function does something else that is not concerning us with the calculation we're trying to do. It needs to be there. Okay, so let's take a look at the problem. I have a quadratic. And I also know where the vertex is. Where is the vertex looking at the equation? 1 and negative 2. This is where vertex is. At 1, negative 2. And you read that from the equation. If you memorize the equation, then you know that this is minus in the original equation, which is y, because now it's plus. We put it as a minus 1. And then this one is 2 units down, right? So you know where the vertex is. And you know that it has negative a, which means a frown, right? A frown. And that's the quick sketch. Now you should be able to do this for every single problem, not just x squared. So let's take a look at a few more examples. It's a terrible line. I can't draw the straight line. Let's call that good. All right. So now I'm going to put a random problem and define the leading term, and then talk from the leading term, see everything else. So eight x cubed minus x squared plus 3. So this is our problem. That's 3. It should be immediately clear that the first term in this case has the highest exponent. So that guy will be called the leading term. What happened? Leading coefficient is part of the leading term. So the entire thing over here is the leading term. And then 8 alone is the leading coefficient. So once I have a leading term, I can copy it again. Leading term is 8x cubed. That's the leading term. And 8 alone is the leading coefficient. So now you look at the exponent of the leading term. You will always have to find the leading term first, and then look at exponents and arrangements, and you see that which end behavior you need to use. It's what do we have? It's odd, right? Because 3 is odd number, and then a is bigger than 0. So let's go find odd. A is bigger than 0. So it's one of these two configurations. Now you know that the one on top is for x squared, and one on the bottom is for x cubed. We don't actually have to do more work. That's it. You know that a is 8, which is bigger than 0. So it should look like this. And I put the break in there. You'll see why I put the break soon. But this is how this problem is solved. I mean, yeah, you can draw a nice, beautiful graph on it, right? Flowers and stuff, arrange it just like you did for your boxes, right? Right? Right. See, if you have many boxes, you can drop into battery.
That's actually
Maybe. Okay, maybe. You decided battery is better option for it, but there you go. When we are looking at the polynomial problem, there will always be a term with the highest exponent. That term with the highest exponent doesn't matter, because what I'm going to do on the test, I'm going to hide it. All right, put it like to be the third one in a string of 5. So leading term is the one with the highest exponent. In this case, it has exponent of 3, 2, and 0. So that's the highest one. As soon as you locate the highest one, that is your leading term. The coefficient of that term is called the leading coefficient because it comes from the leading term. That should be common sense. We are able to pick up that the exponent is odd because we look at it with our eyes. And then we also are able to determine that 8 is positive, right? So we have the combination, because you are memorizing the chart, right? We have the combination which says A positive and exponential odd, they intersect in this cell here, which is exactly what the graph of x cubed is. Does this make any sense? So end behavior should be fairly simple. I'm going to now write something for you guys to consider, to know, and then we'll go on. So, even and odd. It's like a chart. Even exponents, well, 0 is not an even number, but yeah. So we're going to have our constant function here. And then immediately write it as a slanted line. Then we are going to have a quadratic. And yeah. Then we have x cubed, which might look something like this. So this is y equals some value c. This is y equal mx plus b. This is y equal a squared plus bx plus c. bx. Much better. And now we're getting to the cubic one. So y is equal to ax cubed plus bx plus c, no, plus bx squared plus cx plus d. It's longer, right, by one term. And now I'm going to go to the fourth. I'm not going to write equations anymore, but here's a graph for it. So can anyone tell me, looking at these crooked drawings of mine, what's different between this case and this case? What's different between them? Yes, very good. So this is some order of x to the fourth. Excellent, excellent, excellent. It flattens out. So if you can take a look over here, it goes down, bounces right up. This one, what I used to call it when I was a student, it used to hang around longer around your origin. So how do I graph y to the sixth? Wider. Y to the eighth? Wider still. So they're all going to look like x squared. But then you keep stretching them as you go x to the fourth, x to the sixth, x to the eighth, x to the 10th. No matter what exponent you get, you just keep stretching it. Now, to learn this, right, you can take the calculator that you have, probably, the graphing calculator we can do on the test. You take that calculator and then graph on that calculator x to the x squared, x to the fourth, x to the sixth, and you will see exactly this behavior of the higher the exponent, it gets more stretched in that region. So your seat is over there.
Universe is playing games with me today.
And now let's take a look at how y order of y to the x to the 5. Same deal. Same deal. So now look at this. This is like a pattern. It's a pattern. All the even ones, look, both together up, both together up. All the odd ones, diagonally looking always, right? And you can see that cube and the fifth is just wider, just like these. It's very easy and very systematic to remember all of these things. So end behavior for even function is going to look the same way. For odd function, it's going to look in opposite corners. And then for the rest, right, is quadratic, and then x to the fourth wider, x to the sixth wider still, and so on. And you have the same progression for odd ones, where y equal mx plus b, which is the linear, grows into cubic, grows into fifth degree, seventh, ninth, and so on. And every time you add a new one, it's just, right, you go 2 more degrees up, you get to widen your graph. Now, guys, these are sketches. They're not going to be perfectly precise unless you're computing points and plugging things in. But the purpose of this section is to learn how to deal with the graphs, the basic polynomial graphs, so you don't have to go and crank any calculations.
Is it your same pattern for square roots? No?
That's it. So now that we understand this and know how to graph y, here's a challenge question for you. Right out of textbook. Problem 22 says that f of x is equal to 11x to the fourth minus 6x squared plus x plus 3. So try to get the end behavior, and if you don't know what's happening in the middle, just put the dots. All set? So the leading term here is 11x to the fourth. From there I see 11, which is larger than 0, right, as a. And so it's larger than 0, which means default state. And then we have the even exponent. Which means that both of these look the same way, right? When you go to the chart, see even exponents both look the same way. Both look up. Or both look down, depending on which problem you have. So now, all is left for me is to graph. I do this at the angle with the glare on the screen. It's so difficult to make it. So what do I have? I'll go through the origin, even though the function probably doesn't. No, it doesn't. And I'm going to put the end behavior, which must be this. So you put the end behavior first because it can guide the rest of the problem. So now, come on. So now what we're going to do? How do we populate the rest of the graph? Well, you know that x to the fourth is the one that has tendency to stick around longer. I'm just going to move the arrow because it's easier. And that's the sketch. That was quick. So we'll say it goes through 0, it doesn't, but let's say. And then you just want to make it wider than you usually would. And it goes up with the two end behavior. So everything kind of works together. The final piece of this leading term business will be revealed next class or following class, whatever. Because the first term, the leading term, there is something called leading term test, which composed of three different calculations, if you want to call them. So one of those would be the orientation, right? But another one will tell you whether it opens up or down, and another one will tell you how many roots you have. That's the one that we'll be covering later. So the idea of this section is to teach you, to ask you to memorize these basic cases, and then as the exponents grow, it will just keep widening. You're also supposed to categorize these even exponents separate from odd exponents. And that is extremely important because you see that you can sketch the graph for the entire function, right, that you don't know generally how it looks like, just by following these rules. Well, there will be more rules for more precise work coming up, but this is the first sketch, and it's beneficial. So last time I did the experiment. I'll do the experiment again, right? All for science. See? I'm going to toss this marker. It's going to have that parabolic motion like that. So here goes the experiment, right? And that's it. So now, what you've seen as I tossed that marker across the room, you saw this. Now, if you took physics before, or if you plan to take physics, the formula is y as a function of time is equal to -1/2 gt squared plus v0t plus y0. And you see that the leading term is the one with the -1/2 gt squared. Now call G 9.81, which is 10, say. So 10 divided by 2 is 5. So you can literally look at this first term as negative 5x squared. Well, t squared, but x squared. So when you look at that term, and it looks like that, you see that a is negative, and you see that the exponent is even. Even exponent means both end behaviors look the same way, and because it was negative, it will open downwards. And that's what you, again, are memorizing from the chart. So you see a downward for negative a, we had negative 5t squared, or negative whatever. So that's even exponent and this one. And this is exactly what you saw when I throw the marker. This kind of line, right? So that's why we learn all of these things quickly. We can reference, right? So if I throw something that way, it will go into what we call parabolic motion. And now you hopefully understand one of the physics formulas. In order for you to learn physics, guys, just gravity is going to pull it down. So gravity is going to pull it down. You need to have initial velocity, because I can't throw this marker without putting in initial velocity. I'm putting in initial velocity by throwing. If I don't throw this, no parabolic motion. It just drops down, right? So only if I give the initial velocity, which means that my hand was moving, you can calculate that in miles per hour or whatever, right? I'm very fast. If I throw this, right, that's where this V0 comes in, and then you have Y0, which means, right, this is 6 feet throw, 3 feet throw, right? So I can do that. It's still going to be parabolic motion, except now this Y0 was 3. If I use the same strength from higher up, it's going to go further. So those are all the experiments. Yes.
Does y stand for anything like the velocity and gravity, or just?
I'm sorry?
Does y?
It's the height. Yes, it's the initial height. Y0 is initial height, and that's what I said when I'm throwing it from 6 feet or from 3 feet. If I throw it with the exact same initial velocity, the one that I throw from higher will go further, right? So they all. It's physics. It has to make sense. G is the gravity, acceleration due to gravity. Depending on what kind of physics course you have, but later. They're not that, air resistance when you throw something is not that much of a problem unless the shape of something you're throwing is experiencing drag and stuff. But when you throw a stone, it's just negligent. Don't have to worry about it.
Question on the box. That I screwed up making. Do you take into account?
You have to make a paper square first.
No, I know. But would you take into account the thickness of the paper?
Yep.
What if you're using something thicker?
Doesn't matter. It's not gonna change much. All right, so guys, leading term test. So first of all, know what the leading term is. It's the term with the highest exponent. Once you know what the leading term is, you're going to take the look at the a and look at the exponent. A will open up or down, and then the exponent is going to say that both look up if it's even, right? Or they look one up, one down if it's odd. So you have to memorize that stuff. So we talked about the end behavior, we talked about this, and now we can do a little bit better in terms of sketching graphs, because in certain cases, it is very easy for us to determine the x-intercepts, because the graph which goes through x-axis creates an x-intercept, and that's additional piece of information, additional point that you can graph and then make your sketch more precise. So if I just start with y equal x squared, the most basic thing that you can think of, you go and you say, all right, where is the x-intercept? Well, x-intercept happens when I set y to 0, and then I solve this square root both sides, so x is 0. So I see that the x-intercept is at 0, 0. Well, so is y, but cool. Well, I only have one term, which means that one term is the leading term as well, from which I can get that a is equal to 1, and I can get the even exponent. So I take these pieces together, and I can graph the quadratic, because now I have 0, 0, and the end behavior both look up because the a is larger than 0, and they both look the same way because it is the even exponent. So that's what we have. But what we tossed in the mix now is this idea of the x-intercept. So now I'm going to look at the equation that looks like this. Let's say I have x minus 1 times x plus 3. Now we can work this out and see what was the original equation before it was factored. So it's going to be x squared plus 2x minus 3. So this is how it looked like, but we actually want this form. This is cool. Because from here, I can quickly find out x-intercepts. X equals 1 and x equals negative 3. Those are x-intercepts. From this form here, I can quickly figure out that a is equal to 1 and the exponent is even. You see, a lot of information coming in from different forms. And if I am to go and use and do the completing the square, we get the vertex as well, right? So you see that each one of these forms gives you something good for graphing. So what do I have now? I have this crooked line, which I'm going to erase. I said erase. And then draw again. There we go. So I have negative 3 as the x-intercept and a positive 1 as x-intercept. I know that the polynomial should face upward, and I know that both ends look up because it's even. So this is more precise sketch than the one that you would put without the knowledge of x-intercepts. So when you get the equation, you ask yourself, can I factor this to get those x-intercepts? If you can't, well, then it's quadratic formula, right? The negative b plus minus square root. Anyone? B squared. Yeah, it was right there on this board. I know. I erased it. I worked hard. You guys on the vacation? It's like you're just like not into it today, right? No. Like collectively. So let's just cancel the rest of this. Because it's just gonna get worse. Or you can always redo it next semester. It's okay.
It will always be one of those no.
Yeah, because it's 1. Oh, all right. Now let's take a look at a slightly spicier example. because you are so into doing work today. So here is the one that has 3 of these parentheses. And yes, you can do the, you can FOIL the first 2 and then FOIL into, but my argument is that you actually don't have to do that at all. You can just look at this. So what is this? 3 x-intercepts, very good. They are at x equals 1, x equals, and x equals, awesome. So we have 4 intercepts. Now what's A? A is 3, very good. Because that A is always the coefficient of the leading term. Now when you go x times x times x, that's x cubed, and then you have to multiply by the 3. So the leading term is 3x cubed. So there's your 3 there. And what is the exponent? Exponent is cubed. So we have odd exponent. Now how do I know exponent? We'll see later that the number of x-intercepts corresponds to the number of to the value of the exponent. So 1, 2, 3 is 3, but also you go x times x times x is x cubed. So that's the best option. Now it's the time for us to put all of this information together and sketch the best graph possible. So what do I know from these 2 pieces of information? I know the end behavior. If A is positive and we have odd exponent, what's happening? Very good. So the left side goes like this, the right side goes like that. So this is what you memorized from the chart. We have no clue what's happening in the middle from this line. That's going to be determined by this. But from this line, because we memorized the chart, we know that this is the behavior, the end behavior of the graph. So I can now start sketching this because I have information in terms of the intercepts and stuff. So let's go. We have 1, -2, -4. And I have a behavior like this and like that. Isn't it like connect the dots in a good old coloring book, except you don't have to color? Look at this. This one is going to go connect to the dot and then pass and then come back to this one and come back to that. You see how it's smooth motion? Look at the finger one more time. Look, starts here, goes to the first one, goes back to the second one, goes back to the third one and connects there. Oh, but just in time. Look. So we start here at the end, right? And it goes after the first checkpoint, through the second checkpoint, through the third checkpoint, and done. So done, just connect. I like to use a different color to connect this.
How do you know exactly what it's going to mark on that side?
You don't. We're going to leave that for calculus. Calculus section 4.3 to be more precise. We'll deal with that. Unless you change the book for it. So what was the whole procedure for the problem? You had it already in a factored form. Do a little victory dance because that's the top part. You solve each 0, which is the root, or x-intercept, or same names. You know that a is equal to 3. You also know that exponent is 3 because x times x times x is x cubed. These 2 pieces of information, because you memorize the chart, give you the end behavior, which you get to graph as these 2 black arrows, right? And you also place all 3 intercepts in this case, and then connect it in the only way possible. Now the question was, how do we know whether it goes all the way up and then down, or maybe just like, quickly? We don't. Not here, not now, but you are going to have eventually, in calculus course, you take the derivative, you set it equal to 0, which gives you critical value. Critical value is the extrema, either min or a max, which are those 2 points. So you will know how high it goes. But not now. Now it's just a sketch. We are building up to that stuff. So I'm going to do a full review of what we did so far, because the next part is the multiplicity, and I really need you to have that final stretch to understand what's happening with multiplicities, because that, for a lot of students, I don't know, that's confusing, so I hope you pay attention. But let's first review everything so far. We are graphing polynomials. Polynomials can have any integer as the highest exponent, and that term is called the leading term. Now, the leading term will either be even or odd, and then you will have leading coefficient there. So even and odd plus the leading coefficient being positive or negative together in the chart gives you the end behavior. The polynomial will have roots or x-intercepts or solutions. They're all the same name. Different name for the same concept. And what's happening with those is that is the place where the graph will cut through x-axis or bounce off. And we'll see what that means. So now when you are graphing any of these problems, you take a look at all of that information. You take a look at roots. You take a look at value for a, and you take a look at the exponent, and then put together the end behavior first, these guys as well, and then just connect through. This piece now on multiplicity could be tricky, so please pay attention on a double, I would say. So multiplicity of a root happens when you have multiple roots that have the same value. So if I have, let's say, y is equal to, let's go 2x minus 2, and then another x minus 2, and then another x minus, let's do x plus 4 now. So let's say these are the roots. You are observing that you actually have 3 roots, but 2 are the same. So you will say x equals 2, x equals 2, x equals negative 4. But we really don't need the repeat, so I'm just going to call this one, I'm going to say M2. M2 means multiplicity 2. Okay? So these two together create x equals to M2. M2 stands for multiplicity 2. Now, please observe that everything stays the same in regards that our a is now 2. And what's the exponent? 3, which is odd. This information gives me the end behavior, right? So graphing this is going to be a little bit different now. And this is where confusion kicks in, so pay attention. Observe that you only have 2 and negative 4 as values. But you have the end behavior like this and the end behavior like that. So this is your setup. What is happening here? Don't draw this, but I'm going to just try. If I am to go like this and then bounce through this one, I don't have an extra x-intercept to go back and connect into the arrow, right? Like this? No. Yeah, no. So in reality, guys, the solution and what's happening here is that this one over here, and I'll write multiplicity 2, M2. M2 means a quadratic bounce. So you go through this and you bounce off of this one up. I'm just going to say, and I'm going to point at M2 at the same time. Quadratic bounce. This is not mathematical terminology, okay? This is my terminology. So you see what happened. Look, you can put these two together into 1x minus 2 squared. And how do you graph x squared? As a right parabola. So you go through, and then it comes down, and then it bounces off of this one right here, because at 2 you have a quadratic function. Is it cool? How do you pass through the root that has 3 roots? You're going to paste in a cubic fashion with a squiggle. Why you are passing straight through over here? Because a straight through pass is what kind of pass? Is a linear pass. 3x plus 4, like mx plus b, 1x plus 4. It's a linear pass. So we are passing in linear this way, and then we bounce off quadratic. Passing linear, m1, 1 root, m2, multiplicity 2, 2 roots of those, so that's why it bounces this way. It's still a cubic. Yes?
So we just have to label it like that just on the side that there's a bounce.
Yeah, m2. But I see it. I mean, when if you don't learn these concepts and these multiplicities and stuff, it really gets ugly later on. So that's the part.
So if you have
M3, it's the same thing.
No, it passes through, but it passes through. That's what I'm going to make now, a chart of these. So if you have x equals some number, I'll call it c, m1, which means multiplicity 1, which is the standard solutions we had so far, then you just pass through that c. But if x is equal to c as the multiplicity 2, then it's going to bounce off in a quadratic fashion. If you have x equals to c multiplicity 3, it's going to pass through cubic, like this, through c. If you have x equals c multiplicity 4, which means 4 roots have the same answer, then it's going to be the wider. Remember the wider? I don't need this one. It's just c. So the pass-throughs or bounces depend on multiplicity of the root. If you have just one root, it just passes through. But if you have any higher order, it's going to pass through like a cubic, and then the 5th is going to make it wider, and the 7th makes it wider, and so on. I think it's very systematic. All of it. I might be wrong. Okay. So let's take a look at another homework example. And here, try this one. It says f of x is equal to x plus 3, x plus 1 cubed, and x plus 4. Go. So are you done with the? How many roots do we have altogether? 5 roots. How many are repeated?
3.
Right, 1 root has multiplicity of 3. Good. So I have x equals -3, multiplicity 1, which means it's just going to be passed through. I also have x equals -4, which is also multiplicity 1. But then I have x equals -1, and that one is multiplicity 3. What's the leading coefficient? 1. And what's the exponent on the whole thing? 5. Excellent. You guys are getting this. This is awesome. I actually never had a class that was getting that fast. So we have 3, 4, 5. So 5 roots. So that's x to the 5. So the leading term, LT, is x to the 5. We know that a is equal to 1, which is bigger than 0. This is odd, right? Exponent. So we have this kind of behavior. Let's draw. -3, -4, -1. And we have to have this kind of behavior. So now with the blue, I will go straight through -4, bounce back straight through -3, and then cubic. Yeah, you have to cubic through. I know. Because the -1 is the m3, and m3 means it's a cubic, and you can also see it in the equation. It was raised to the 3rd power. And if it's a 3rd power, right?
So you have to make sure it curves going to -1.
Yes.
On the bottom side.
Because -1 is the m3.
How did you get the M3 on the -1?
Because that, if you look at the setup of the problem, that's the one that had the cube on it.
Oh.
Right? So cube means 3 solutions of the same kind. You can write it as x plus 1, x plus 1, x plus 1, right? So that's 3 -1s. That's why we just write m3 rather than listing 3 of them.
So when you're writing like you're writing -1 M3, what's the proper way to write it? You don't put -1 and then M3 like right next to it. Or you
That's
leave
what I
a little
did.
Space.
Yeah, level space. Yeah, yeah. Level your space, but m3 is just as multiplicity, so you don't have to spell it out.
Okay.
Or, so you don't have to write that root 3 times. It's just a shorter notation. Another one?
Yeah.
Of course, another one. You love this stuff. You're gonna go home now and do another 7. No. Good luck. Discuss this with your friends and colleagues over here.
It should be more like a colleague than a friend.
Sure. I'm worried if you're not comfortable enough. You do the problem?
Yeah. Like, I'm not sure if it's right. No? Is it right?
Nope.
But then. Yeah, so when they're x equals 2, x equals 3, like 1 is like x equals 1.
No, it's just all the things I have in my car. Oh my god, what a
People there.
No, it doesn't just go back down. It, like, wherever you leave it, then it goes up. No, it's being function, but it's negative 1.
Yes. Okay, let's take a look. It looks like that majority of you has this, which is awesome. So, x equals -1 multiplicity 2, x equals 2 multiplicity 3, and x equals -4 multiplicity 1. We also have the leading term, LT, to be equal to -2x to the 6. X to the 6, because you have 6 x's, guys. You have 6 x's on a pile. There are 2 x's, and 3 x's is 5 x's, and 1 more is 6 x's. So now what we know from here is that a is less than 0. We have even exponent, so that tells us the end behavior looks like this, which is what we memorized from the chart. Otherwise, you're doomed. So now we need to put the rest together just by looking at those intercepts. So we have intercept at -1, intercept at +2, and intercept at -4. And we have the end behavior to look like this. So now we fill in with the blue. Please look at the screen if you're still confused, because I'll talk as I draw. So once I have these two, I start with the -4, and -4 is M1. M1 means linear pass-through. Linear pass-through, straight line through. And then the next is -1. -1 has M2. M2 is a quadratic, so it has to be a quadratic bounce. So we're going to bend down and then bounce through -1. And then we're going to take a look at the last one, which is x equals to 2, which has M3, which means cubic through. And it connects down. So here's your straight line linear through, quadratic bounds, and the cubic through. Cool, right? All right, so what we're going to do now, since I see you guys are a little bit restless, is we're going to take a short break. And then when you come back from the short break, we are going to do the intermediate value theorem, and the lecture is done. This is one of the longer ones. So we still have one more concept to cover. So mandatory break. And then, yeah, and then we'll see the line for the bathroom is 70 people. I didn't want to do this. It's kind of like
Wait, you saw the guy in the cafeteria? He looks just exactly like you.
Oh, hey.
Yo! Oh my god!
With the
Yeah!
bun?
I was
I was
like,
actually looking at him.
yeah,
He's bun.
he was sitting right next to me, and then when he walked, I was, is that him? And I was like, and then you saw it there. I'm like, what's going on? And he got the red shirt. It was so funny. You guys had the same height. I was like,
no, okay, it could be. It's just like, well, maybe it's on a different page. Like, stop being a dumb shit. Yeah.
Where did you get your shirt from?
It's in clicks.
Oh, where it's like, what is the data in terms of like individuals? It's more, if you live towards like, you're in a more cultured area where you eat more cheese and dairy products are more in your diet. So the more you're exposed to it, the more likely it is that you're going to be intolerant to that.
I know.
Just like follow the higher curve for someone that will that's intolerant and on the lower one you can make it curve that goes down and then it's lower.
See you, Professor.
See you later.
And then the person who is digesting glucose, so it's a higher
I think my dad went to a farm. I'll just walk there. Oh, really? I don't go there right now. Well, by Zoom, it's not. I mean,
I literally I've done like 4 of them.
Alright, we're starting in 1 minute.
You have to pair it, so don't pair it yeah, you say it keeps opening new, like they keep walking like that.
yeah, right? It's needy happening.
Because it's also a function. No, no, it's. I didn't like work person.
But I do like
Like, X press, like, I would say, press harder. Yeah, with that quiz. I got here like an hour early. It was this thing.
Thing is still in development.
Yeah, but then I sat down next to it and then
Whatever you say is take that result. Just have subject and object and then compare.
I didn't learn this. You, if you were a science teacher, you actually probably use chemistry. You use one
Let's take a look at the last concept and call it a day. So the last concept is intermediate value theorem. This is featured on your labs. And it could be a little bit long for calculations and so on. Let's take a look. So the intermediate value theorem is for the polynomial functions. It's given on page 325. It reads, let f be a polynomial function with real coefficients. If f of a and f of b have opposite signs, then there is at least one value c between a and b for which f of c is 0. So this is technically a theorem which tells us that there is a 0 for the polynomial. I'm going to draw a random pass-through, as you can see. And if I pick two values on x-axis, value a and value b, look what's happening here. This point here is a f of a, and this point here is b f of b. So these are the two values that we get. You can see that at this value c is in between a and b, and its value of f of c is 0, which means it's a root. By picking random values systematically, we can actually figure out, to whatever precision we want, we can figure out what is the where is the root, because we can keep calculating, finding one after another decimal point, which is what the algorithms do when you want to find the root, let's say using calculator. So let me work out an example hopefully you understand at least a portion of it, and then, you know, suffer through the lab, and it will work out eventually somehow. So whatever, it really doesn't matter which one we pick. Let's go with problem 38. They say that the f of x is given as x to the 5 minus x cubed minus 1. And they tell us that we should look on the interval 1 to 3, no, 1 to 2. Interval 1 to 2. Now, if I am to draw this, I'm just going to draw like this. This is number 1, this is number 2, and somewhere in there, there is the unknown c, which is actually the root. So this is what the setup of the problem is. Yeah, there is a whole function around it, right? There is this x to the 5, which is going to, you can do all of the stuff that we learned earlier. But we are only concerned to actually, we are concerned with finding the value of c so that we can draw the graph. Now, how is that achieved? Well, as long as when you're computing these endpoints, so f of 1 and f of 2, as long as one is positive, the other one is negative, it's guaranteed that they are around the root. So now, let's figure out f of 1. F of 1 is clearly 1 minus 1 minus 1, which is negative 1. And f of 2 is 2 to the 5, which is 32, minus 8 minus 1. I don't even need to compute. I see it's larger than 0, and this one is smaller than 0. So this is a confirmation that the root is between 1 and 2. Now what we are going to do is we are going to pick half of the interval. So I need to find how much is f of 1.5. What am I doing? I am picking half of the interval, and as you can see, the root is going to be in one of the two places. So I'm picking 1.5, and then you can use your calculator to compute 1.5 to the 5 minus 1.5 cubed minus 1, right? So you use that. So let's go. I'm going to. So I know that this is not allowed on the test, right, to use the graphic calculators, but you can use them, right, for the labs and stuff. So I have 1.5 raised to the 5 minus 1.5 raised to the 3, and then minus 1. And I have 3 point. It really doesn't matter what you get. It's just important it's bigger than 0. All right, so now look what you have. You have that you need larger than 0 and smaller than 0. So you want to keep 1.5, and obviously you will have to pick 1. So with this calculation now you know that your root is in between these two values. So you technically zoomed in. So now you can compute either f of 1.2 or 1.3, whatever. Doesn't matter. Pick one. Let's say 1.3, whatever. How much is f of 1.3? Compute again in a function. So 1.3 raised to the 5 minus 1.3 raised to the 3 minus 1 is 0.5. That's bigger than 0. So now you have to pick, again, f of 1 and 1.3. See, you are zooming in. You are zooming in on the solution. I don't know, pick 1, 1, pick 1, 2, doesn't matter. Which one we want to pick? 1, 1. Compute at 1, 1. So you keep playing this game. 1.1 raised to the 5 plus, no, minus. 1.1 raised to the 3 minus 1 is negative 0.7, less than 0. So now look, 1.3 is bigger than 0. This one is less than 0. That means that we zoomed in, it's between 1, 1 and 1, 3. So now you have to pick 1, 2. And you will know the first decimal. So now when you compute 1.2 to the 5th minus 1.2 cubed minus 1 is again negative. Awesome. So now we are going to obviously replace 1, 1 because we have a better number. So now we know that the solution is on 1.2, between 1.2 and 1.3. But realize that every single number between these two numbers starts with 1.2. So you can start compiling your solution. It starts with 1.2. Now, f of 1.25. See? You're adding a decimal now. You compute that. And you can drill with this for the in eternity, your entire life. You can just keep adding these decimals. You will be discovering the next digit, the next digit, the next digit, the next digit, and you can go as long as you have the stamina or until your batteries run out. Calculator, and then you have to go and get the new battery. (1.25 to the 5th power minus, or you can ask Taylor to get your battery. She's good with that. So this calculation gives us 0.099, 0.1, which is larger than 0. So we are going to use less than and larger than, right? Because you know that at 1, 2 is less than, at 1, 3 was larger than, so you're scrapping 1, 3. So you are at 1.2 and then 1.25. And then you pick a value in between, and a pick value in between, and pick value in between, and you can go like this until you figure out, I don't know, whatever number of decimals you want. Have fun with these calculations. And I will see you all on Tuesday for the next section.